This is the backstory for the law of cosines. Where did it come from? It did not, in fact, fall out of the sky and hit Pythagoras in the head or anything like that. It has a story all its own. So I'm going to make a coordinate system here. Got my origin there. And I'm going to put a triangle in here. It's not a special triangle in particular. I'm going to put it so that one of its sides is sitting on the x-axis, and it's an oblique triangle. That may look like a right angle, but it's supposed to not be an oblique triangle. So I'm going to call this angle at the origin A. Yeah, any triangle that you want to draw anywhere, you can turn around so that it sits with one side in the x-axis. So this is an arbitrary triangle. The other vertex in the x-axis I'm going to call B, which means this side up here is C. I'm in a coordinate system, so we can name these points. A is the origin, no problem there. Let's see. The side across from angle C, we traditionally call little c. Actually, we might as well put little a and little b in here too, opposite their respective angles. Now that I named this distance little c, I can put some coordinates with point B. Point B is on the x-axis, so its y-coordinate is 0. I have a distance of C that starts at the origin and ends at B. That tells me the y-coordinate here of point B, I could call C, that length from the origin over to B. Point C up here at this angle, I'm just going to give some arbitrary, we'll call it x comma y. Let's see what else we know. I want to put an altitude in here. So I'm going to go from angle C down to the opposite side. By definition, an altitude makes a right angle with the side that it runs into. So I have this altitude that goes from point C down to the x-axis. This distance, starting at the origin at point A and going to where my altitude hits the x-axis, well, that's a point directly underneath this point, x comma y. So this distance must be whatever the x-coordinate of point C is. That would be x. We can do the same thing in this direction. My altitude goes from the x-axis up to point C. So this length must match the y-coordinate of point C. Started at 0, went up to the point. That distance we could call y. Something else that happened when I put this altitude in is now I have a right triangle to the left of the altitude. So I can talk sines and cosines in that right triangle. We'll look at angle A down here at the origin. I could say the sine of angle A is its opposite side, which we're calling y, over its hypotenuse, which is side little b of that right triangle. Well, y is a pretty generic name. I would like to solve this for y, and I get b times sine A. The reason that's good is now I'm expressing this y-coordinate of this point using parts of the triangle and not just arbitrary y. We can also talk about the cosine of angle A. Its adjacent side, which is x, over the hypotenuse, which is still b. And I can solve that also for x. X is b times cosine A. And again, that's good because now instead of just arbitrary x, I'm naming point x in terms of parts of the triangle, sides and angles of my triangle. So I could call point C now b cosine A, comma, b sine A, which is a little bit better than just x and y. One other thing we want to call back to mind before we launch here, we haven't launched yet, this is all just laying the groundwork, is the distance formula. This is probably something you've known for a long time. Just so you don't have to dig it up, here it is. Distance formula based on the Pythagorean theorem. So the difference of the x coordinates squared, difference of the y coordinates squared. I'm going to add those together, take a square root, and that gives me the distance between 2 points. Why do I care about that? Well, that's what we're going to use. I would like to talk about the distance between B and C. Distance between those 2 points. Well, we actually have a couple different ways we can do that. One of them is it's A. It's the side of the triangle opposite the angle that we named A. The other way is by using the distance formula. The distance between B and C, the difference of their x coordinates, squared, plus the difference of their y coordinates, squared, the square root of all that. So distance between B and C, distance between B and C. I have two different names for the same thing, two different expressions for the same quantity, so they must be the same. If they're expressing the same quantity, those two expressions are equal to each other. I don't really want to go through the next several steps here, writing that giant square root every time. So what I'd like to do is square both sides of my little equation. There's no problem with doing that. We can do the same thing on both sides of the equation. If the distances are the same, their squares are the same too. What the effect that's going to have on the right is I don't have to write that square root anymore. At the same time, I'm going to use these expressions for x and y that we found up here. I'm going to use b sine a for y, b cosine a for x. Again, so that we're expressing everything in terms of parts of this triangle. So there's x minus c squared. I'm not going to put minus 0. Y minus 0 is still y. So squared both sides, made some substitutions. Now we're going to do a little algebra. So I'm going to square this out. And I got a squared equals, let's see. So the first thing squared, the b is squared, the cosine is squared, and then minus 2 times the first times the second. Multiplication is commutative, and I like it better that way, so I'm going to do it that way. Plus the second thing squared. And if you forget how that goes, go ahead and write it out. This is b cosine a minus c times b cosine a minus c. Multiply it by itself. Plus, here I'm going to have, this is just one term, so the b gets squared and the sine gets squared. Now, algebra is still at work. I'm going to notice I have two terms that have a b squared in them. I have b squared cosine squared a, b squared sine squared a. So I'm going to move those closer together and factor out that b squared. From my first term, I got cosine squared a. From the second term, I got plus sine squared a. I'm not going to do anything with any of the rest of that stuff. It just follows along here. Now, you may recognize an identity right here. Cosine squared a plus sine squared a. Pythagorean, there it is. Pythagorean identity, that's 1. Why am I going to write b squared times all this when I could just write b squared times 1? I'm not. That's just b squared. Plus c squared, just rearranging. And that is our law of cosines, version 1. If I had labeled differently from the beginning and done the same things with the labels in a different order, I might have solved for B. Or C. So law of cosines, pick your favorite version. I'm going to point out here a couple things. First of all, I can use the law of cosines when I know two sides and the angle between them. That would be side angle side. I can also use the law of cosines if I know all three sides of an oblique triangle. ABC, there's B again, C again. The only thing I won't know is the angle. So that's what the law of cosines is useful for when I have either one of those types of information. I'm also going to point out if the triangle happens to be a right triangle, so that my angle is 90 degrees, the cosine of 90 degrees is 0. So if I'm in a right triangle, this whole last term becomes times 0, and we get the Pythagorean theorem as we have known it for a long time. So it's consistent with everything we already know.